Today, we want to shore up our understanding of operations and how we use them and how we write about these operations so that we can incorporate trigonometric functions into our operations. So we're going to start with the operations, then we're going to talk about the order of operations, which is going to be not PEMDAS. Then we're going to talk about reading expressions, and then we can talk about inverse operations. Then we'll see how trig functions get incorporated into this. When I talk about the operations, I'm talking about the big three that we learn about. The big three operations: addition, multiplication, and exponents. These are the big three operations that we deal with: addition, multiplication, and exponents. You might notice that there are a few missing from this. There are lots missing from this, but the two that stand out are subtraction and division. Subtraction is just covered by addition. Division is covered by multiplication. So subtraction goes with addition. And division will go with multiplication. Other ones that you might be familiar with are things like square roots, radical expressions. Radicals go with exponents. So radicals are just exponents. So here are the three big operations: addition, multiplication, and exponents. Addition is our foundation for everything. This is where it all starts. This is what we're going to build these three operations out of. I want to build this out of addition. Here are the rules for addition. We only add things that are the same. When we add them, it doesn't change what they are. Those are Leach's rules for addition. We only add things that are the same, and when we add them, it doesn't change what they are. We only add things that are the same, and when we add them, it doesn't change what they are. This may seem like it's going back pretty far to talk about addition when you're these advanced trigonometry students. But we're trying to build algebra on top of a foundation of arithmetic that has some pieces missing. And that's why things start falling apart. So we're just going to go in and kind of fill in the cracks. One of the fun things to do is ask people to explain how counting works. Not just count to 10, but explain how counting works. And when you start thinking about how you would explain how counting works, it becomes kind of difficult. So let's try to figure this out. We only add things that are the same, and when we add them, it doesn't change what they are. Now, there's lots of different interpretations for sameness. So we just need to increase our interpretation of sameness. There's lots of different kinds of sameness. If I have $5 plus $3, I can add the 5 and the 3 because they represent the same things. $5, $3, and what do we get? $8. It wasn't a trick question, right? It seems like a trick question because like, oh, hang on a second, this feels like a trick question. No tricks. This is just $5 plus $3 is $8. We get to use addition because the 5 and the 3 both represent the same thing. It's $5 and $3. On my desk, if I have 5 pens, if I take out 5 pens and I add 3 more pens, then what do I have? 8 pens. I can add the 5 and the 3 because they both represent pens. And when I add them, it doesn't change what they are. They are still pens. And there are actually still 8 of them. If I have 5 ounces of coffee in a cup, and the waitress comes along, warms it up with 3 ounces of coffee, what do I end up with? 8 ounces of coffee. We can add the 5 and the 3 because they represent the same thing. We only add things that are the same. And when we add them, it doesn't change what they are. This happens in a lot of ways that become more confusing because it becomes less real. The more abstraction we place, the less real something might become. But this is how we deal with expressions in algebra. If I have 5x and I'll add 3x, what do we end up with? 8x. I can add these because they're the same. They're both x. And when I add them, it doesn't change what they are. 5x plus 3x is 8x. Any questions? No, simple, straightforward, right? But still, when we first start learning algebra, it sometimes comes across as some kind of mystical, weird thing. And so 5x plus 3x is 8, I don't know, x squared. We think we have to do something because we don't understand that this is just addition. And when we add things, we only add things that are the same. And when we add them, it doesn't change what they are. So here we've discovered some sameness. It's the same variables, but the variables have to have the same exponents. So if I have 5x squared and 3x squared, what do we have? 8x squared. In algebra, sameness is like terms, and like terms are the same variables with the same exponents. So in algebra, we're dealing with like terms. Sameness is like terms, which means same variables with same exponents. We're familiar with a lot of different kinds of sameness. If I want to add a couple of fractions, let's say 5 over 11, and I want to add 3 over 11, what do we get? 8 over 11, The over 11 part is telling us what kind of fractions. That's the denominator. That's the denomination of our fraction. So an over 11 is the same as another over 11. So I can add them because they're the same. And when I add them, 5 plus 3 is 8. I add the numerators because that's how many of there are. We're enumerating how many there are of this kind of denomination. So when we add them, it doesn't change what they are. 8 11ths. Sameness in fractions is common denominator. Sameness in fractions is a common denominator. How's everybody okay? Of course, the most complicated thing we've done today is 5 plus 3 equals 8. But it's the thinking that goes along with it. If I have $5 and 3 pens, what do I have 8 of? Nothing. Those aren't the same. So I don't add them. I don't have 8 of anything. We don't get to add. These things are not the same. These things are not the same, so there's no addition of that allowed. We don't have 8 of anything. If I have 5x plus 3y, do I have 8 of anything? No. I can't add these. They're not like terms. That's sameness when it comes to these algebraic expressions. We don't have 8 of anything. Now, if I had values for x and y, then they would both just become numbers. I'd be able to add them up and everything would be fine. That would make them the same. I would evaluate them, give both terms a value. Then they would be the same. I can add them up. But right now, 3x and 5x and 3y, can't simplify that. There's no additional out. We can't simplify. That's as simple as it gets before we start putting values in. What about 5x squared plus 3x? Also not 8 of anything. They're different things. We can't add things that are different. These are also not like terms. They have the same same variables, but those variables don't have the same exponents. One's an x squared term, the other one is an x term. The terms are not like. So no additional out, we can't simplify. Any questions? Remember, all the variables have to match before we add stuff. So if I have 5x squared plus 3x squared y, can I add them? No. I don't have 8 of anything because one of these terms is an x squared term, the other one is an x squared y term. They don't have the same variables with the same exponents. Once we have values for X and Y, then we can plug those in, turn everything into numbers, then we can add. But as it stands, we can't simplify this expression anymore. There are some special cases. Sometimes we can get around things. Can I add them as they are? Well, actually, we have a calculator that can do that. So yes, but no, that's not my point. That's clearly not what I was talking about. We can't add them as they are because sameness in fractions is the same denominator. One of these is in denominations of 11. The other one is in denominations of 7. This is like saying if I have $5 and €3, how much money do I have? We don't have 8 of anything. Unless it's some weird day where the dollars are equal to the euro. But we can convert these to have the same denominator. So we can't add them as is, can't add the 5 plus 3 as is. Because we have different denominators. But if we convert the fractions to the same denominator, if we convert our dollars to euro or our euro to dollars, then we can add the things. We can make them the same. And we have one of our favorite math tricks. We just multiply by 1. Oops, 3/7. I spelled 7 wrong. So I'm just going to convert from dollars to euro. So 5 times 7 is 35 over 77. 3 times 11 is 33 over 77. Now we can add because we have the same denominators. But we're not adding a 5 and a 3 anymore. With fractions, we can convert them to have the same denominator. So we can convert fractions to a common denominator. Then we can add. So just like if we have $5 and €3, we can convert our euro to dollars or our dollars to euro, or convert both of them into pesos, and then we would be able to add those numbers. But it wouldn't be 5 and 3 anymore. It'd be like 35 and 30. Questions? We just rules for addition. We only add things that are the same, and when we add them, it doesn't change what they are. Already implied in this is how we indicate a bunch of something that's been added together. And that's part B, or that's 1B, multiplication. Oh, we should make a note about subtraction. So subtraction is included with the addition. Subtraction is addition of opposites. Subtraction is just addition of opposites. Opposites are additive inverses. Inverses under the operation of addition. Connected to this idea is the additive identity. Our operations of addition and multiplication have an identity element, which means if you do the operation with this element, nothing happens. Adding 0 does nothing. And inverse is what you do, what you include under that operation to get to the identity. So 5 has an additive inverse of -5 because 5 plus a -5 gives us 0, the additive identity. Any questions? This is extra language that we don't really need right now, but it's there, and y'all are adults, so you get to hear it. And you're like, oh, we're not in a place where we want to get to hear stuff. We're still in the place where we have to hear stuff. Well, fair. That's fair. You're adults, so you have to hear it. So that's addition. We only add things that are the same, and when we add them, it doesn't change what they are. B. Multiplication. Multiplication is repeated addition. Multiplication is repeated addition. And for notation, we use a coefficient. Multiplication is repeated addition and uses the coefficient slots. So if I have 3 5s added together, they're all the same. We get to summarize this with addition, or sorry, with multiplication. Five plus 5 plus 5 is 3 times 5. We multiply by the 3. In the case of algebraic expressions, that will show up at the 3 will show up as the coefficient. So if I have, say, x plus x plus x, I can say I have 3x. I knew that we knew this because we were doing it on the previous page. When I said 5x plus 3x, you saw 5x's and 3 more x's. That's 8x's in total. We were able to add them because they were the same. Sometimes we forget about these things because we start looking for patterns rather than understanding what we're writing. X plus x plus x is 3x. 3 is the coefficient. It's just a number, a constant that we multiply by. Any questions? Is everybody okay? Everybody's like, oh, yeah, of course, this is algebra, and we've got algebra. Like, oh, so far. We will find some algebra that we may have forgotten. There may be some thinking about algebra that we may not remember, mostly because we don't do algebra a lot. I think about the classes that I teach on a regular basis for the last 20 years, algebra, trigonometry, and calculus. The reason that I remember all these things is not because I've just always remembered all these things, but I talk about them every semester. I talk about calc for a long time. There was about a series, about 15 years where every single semester I did Calc 2. So it's not surprising that I'm good at Calc 2 because I've been doing it over and over again every semester. That makes sense? I mean, that's just how we get good at things. We do them over and over again. I'm very bad at basketball because I have done 0 basketball for a very long time. And by for a very long time, I mean like 51 years. You know what I mean? Just got to be realistic about what you can and can't do and are not able to help people with. Like my goddaughter was like, oh, hey, Uncle Evan. I'm not actually the uncle, I'm the godfather, but she didn't want to call me godfather because she had seen that movie, even though she was a kid. We took her to probably movies that she shouldn't have gone to. She turned out okay. She's like, oh, hey, can you help me with basketball? And I'm like, well, I absolutely cannot help you with basketball. I will totally go to the basketball and bring the basketball and I will give it back to you and stuff like that. But I do not have any instruction on that regard. I am very bad at basketball. You know what I mean? I didn't get mad. I didn't let my ego get in the way. But then you see parents getting all mad because they can't explain their math to their kids. Oh, he's only in the 4th grade. I should be able to explain the math. Yeah, but you can't, so just don't. Just suck it up. Toss your ego and say, sorry, kid, I can't help you. I will support you and I'll bring you cookies and milk when you get mad. And I'll make sure that if you do get mad, it's like, well, hey, kid, let's walk away from this for a little while and go have some cookies and milk. And we can talk about that, but I can't help you. You know what I mean? But then you're like, oh, it's just 4th grade math. How come I can't do it? So I go, well, you suck at math. And that's okay. I suck at basketball. Very bad at it. All right, kid, take the sphere and throw it in such a way that it goes through that circle. So how do I do that? I don't know. Throw it thousands of times, and I bet you'll be good at it. I'm going to be over here having some coffee. Why does your coffee smell like whiskey? Quiet, kid, throw the basketball. I guess I'm not a good basketball coach, is what I'm trying to say. What are we talking about? Oh, yeah. Also, the one time she asked for help in math, it was like an emergency, like right before she had a test the next day. I suck at that too. That was like the worst test she ever had. So I need more time than a day to fix math problems. But that's all right. So what are we talking about? Oh, Multiplication is repeated addition to use coefficient. Notice that in my addition where everything is the same, we can summarize that with a coefficient and summarize repeated multiplication, summarize repeated addition with multiplication. Here's a case of multiplication being used to represent repeated addition. We know that a linear function has a pattern of repeated addition. This says start y at b and add m a bunch of times. Start at b. Add m a bunch of times. So if I add 3m 3 times to the b, then it's b plus 3m. That's the number, x is the number of times we've added m to b. That's how we think about linear functions. That repeated multiplication is summarized with, that repeated addition is summarized with multiplication. Other thing about multiplication we need to know is how it interacts with the other operations. Multiplication distributes over addition. This is how we're thinking about things. We need to think about this because parentheses is not an operation. A lot of times we see this as the distributive property. There's not just the distributive property, it's one distributive property. Multiplication distributes over addition. Here's how we write it. We normally write a parentheses b plus c and say that's ab plus ac. This only works because the operation between a and that set of parentheses is multiplication. It's not the parentheses that are doing it, it's the multiplication that is doing it. And if I sound like I'm getting mad about this, I totally am, because this is one of the biggest breaking points in algebra. We just start saying PEMDAS, 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 and we see the parentheses and go, we know how to deal with this, and you distribute things that aren't multiplication. This works because this is multiplication. And when we split it apart, it's multiplication. I didn't leave enough space. I never do. And it's because our style of writing multiplication is just to jam things together. I'm like, well, maybe we should like always include the operation in between. And everybody else is like, it'll be fine. And it's not fine. So we refer to this as the distributive property and ignore the fact that it's trying to represent multiplication distributes over addition. So I want you to replace in your mind the phrase distributive property with multiplication distributes over addition. It's multiplication. That's why we get to do this. It's not the parentheses that make the distribution happen. It's the fact that it's multiplication. So just thinking of distributive property leads to things like this. Natural log of the sum of x and y is not the sum of the natural log of x and the natural log of y, because it's not natural log times the sum. It's not a multiplication, so we don't get to distribute. It's not multiplication, so you don't get to distribute. We don't say natural log times x plus y. It's natural log of x plus y. A natural log does not distribute over addition. Functions that we have, some new functions that we have this semester, like our trig functions, also not multiplication. So if we have sine of x plus y, this is not the same as sine of x plus sine of y. It's not sine times x plus y, it's sine of x plus y. We don't get to distribute because it's not multiplication. It's multiplication that distributes over addition. That's it. One thing. Here's another one. However, if I have, say, x plus y over z, that is x over z plus y over z. Multiplication distributes over addition, so does division, because division is multiplication by reciprocals. I guess I wasn't ready to write exponents. Division is multiplication by reciprocals. Division is multiplication by reciprocals. Just like subtraction is addition of opposites. Reciprocals are multiplicative inverses. There's that inverses word again. The multiplicative identity is 1. One is the multiplicative identity because it doesn't do anything under the operation of multiplication. When you multiply by 1, nothing happens. Just like 0 is the additive identity, because when you add 0, nothing happens. So what is the multiplicative identity? A reciprocal or a multiplicative inverse is what you multiply by a number to get to the multiplicative identity. Is everybody okay? No, at this point, when I'm talking about operations, no one is okay. It's like, oh, how much structure can you talk about? And I'm like, oh, dude, how much time have you got? Difficult because you try to teach all this arithmetic to you when you're like little kids, and you can't have all this boring detail when you're little kids. Instead, it's just a bunch of boring operations and stuff that you have to memorize. And like half the class gets it instantly for reasons that we can't fathom, and the other half the class struggles with it, once again, for reasons that we can't fathom. Like the one thing that we know about the way human beings learn stuff is that we all learn at different rates and in different ways. So what is the model that we use to teach people stuff? Put a bunch of them in the same room and teach them at the same rate, the same stuff. It's like, oh, that's like the opposite of the way people learn things. It'll be fine. You know what I mean? Are they going to want to do this? No. We're going to have to do this against their will. So we're going to make it fun? No. We're going to make it awful. Does anybody learn how to play recorder when you were in like grade school? I don't know what the young people's grade school experience is. I don't know if there was like a music program where at one point they bought this box of like little recorders, and you all learned how to play hot cross buns. If you spent more time doing that, you would have been better at math. And you might not have to hear me talk about this. So when your parents and they're saying, well, we're worried, we want to cut the music program so we could supplement the math more, tell them that you need to supplement the math program by keeping the music program. It'll be better. And when they're like, oh, we want to teach our children coding, because that's a big thing right now, teach people to code. You should be supportive of that as parents. And when they're like, oh, we're going to replace foreign language with coding, say, except for that. Don't get rid of foreign language and replace it with code. Get rid of the algebra class and replace it with code. Code won't help you speak to other cultures and learn about other cultures. Code will help you understand algebra better. So, good on schools for teaching coding, bad on schools for thinking that it's a foreign language. It's a math class. Get rid of the stupid algebra class. Replace it with a coding. And they'll be better at that. Because one of the other things that gets on the chopping block when a school starts doing poorly in math is foreign language. And then so you get a bunch of Americans that live their whole lives in California, still don't speak Spanish. My Spanish is awful. If I travel, I have to rely on Spanish-speaking people understanding English. And I lived in California my whole life. You know what I mean? All right, let's take a break. Come back and we'll talk about exponents. Pause video.